And we are continuing in 6.1, the final video. This should be pretty short, actually. We're going to look at solids, what's called solids with known cross sections. I think they start with this in your book. It's something to know. I will focus on the revolutions, but you still need to see this. And you'll see a similar theme when we do this problem that you've seen before in Calc 1. So let's take a look at an example to demonstrate this. Find a volume of a right pyramid with a square base. So here's your square base. And altitude h. So really a pyramid, of course, looks like this. Then you have the pyramid shape. It turns out, so you could take this thing and put it put it like this, and it might look like a pyramid, right? But it's easier to do this on the side, like that. Okay, so we're going to look at it like that, and then consider this, we're going to cut this and kind of through here, like kind of let's chop it through, right in the middle. So right there, like that, and see what you get. So draw this next. I drew this ahead of time. So draw an axis. So this would be like your x-axis. This is 0. And then the height, you can see, is from here to here. So the height of that is h. So we don't know what that is. Okay, because it says altitude h. So that's the altitude is from here to here. And then we know the base is a square base. So if you cut right through there, then you know that this side is a half a. And then this is h. So we can use similar triangles, basically this triangle and this triangle, to set it up. So a couple things. Let's look at the cross section. I drew the cross section already. This is the cross section. So you have your thickness, which would be basically like that. So there's your delta x is your cross section. And so what's the area of the cross section? So a cross section is a square of length what? Well, if this is now the cross, let me be clear, try to be more clear on this. The cross section moves. So as you go across, the cross section moves, right? And so you're looking at this one, this one, this one, this one, this one. So what you're doing then is looking at from here. Let me draw this different color. These are the colors that show up better on the darker background, by the way. That's why I have it there. So this is kind of where you're at in the middle. And so the whole length is not just, so that would be like a y. But it's two of them. So 2y gives you the full area. So it's 2y. Oops, let me change colors. So whatever y is here, you have two of them to give you that length of a side. So area in terms of x is 2y squared. Now that's not, we need y in terms of x. Or we say 4y squared. So now find y in terms of x. That's what that triangle above is going to allow us to do using similar triangles. So using similar triangles above, we can say y is to x as what is to what? As 1/2 a is to h. And then solve for y. So y is equal to y is equal to a times x over 2h. ax over 2h. Okay. So then we want to sum up the volumes of the rectangles. So we're gonna sum the area and then times your delta x. So you're going to add those up, right? So your delta x takes care of the height. So it's really the area of this thing that you're looking for. Well, the area is this. It's 2 times y, where y is this. So what you get then is you integrate that. So volume is the integral from 0. Now, where are you going? You're going from here to h along your x. So that's 0 to h. And then it's 4 y squared dx. And so you substitute in for y. So it's 0 to h. And then y is ax over 2h squared dx. And so we can simplify that, and your a and your h are constants, so you can just factor those out. So you end up getting a notice here, you get that's a 2 and a 2, so it's 4 is gone because of that. And so you get a squared over h squared, which factors out. So you get a squared over h squared. Did I say a? A squared over h squared. Integral from 0 to h. And then it's x squared dx. Well, there you go. I mean, that's basically 1/3 x cubed, and then you do h minus 0. So pretty much straight up from there, we got it. So it's equal to a squared over h squared, and then 1/3 x cubed evaluated from 0 to h. And so that's a squared over h squared times 1/3 h cubed. Do a little simplification, and you get 1/3 a squared h, which if you looked it up in a formula table, that's exactly what you would get for volume of a pyramid. It is 1/3 time, if you have a square base, it's 1/3 of the area of the side squared times the height. So that's, I mean, basically this is deriving a way to derive the volume of a pyramid before you even though, so in the history speaking, you could, they would already know the volume of a pyramid, but this is the calculus way to basically prove it or show it. And that's another theme that we will see is known formulas from other methods can be shown by using calculus.